We want to understand the world, what is the source and the origin of our existence.
Carbon-12 is the essence of life, the element which forms the basis of our life on Earth.
The Hoyle state is the only named state, nuclear state, right? Which tells you how important it is. We haven't bothered to give a name to anything else. Everything around us that's heavier than helium was made through the Hoyle state. And knowing how the Hoyle state decays tells us how much carbon is made in the universe. And knowing how much carbon is made in a star really helps us understand our stellar models, because if you put a different decay rate that Tibor found that's 34% higher, then you change the amount of carbon that's produced in a star. So it's a big deal.
For many years, physicists were puzzled how carbon is made in a universe. And turn out it is happening in a very rare process when three alpha particles collide in a center of the star and form carbon-12. In the center of the star, in a helium burning cycle, there is lots of alpha particles together, very high temperature, very high pressure, and they can fuse together and form beryllium-8. But beryllium-8 is unstable. So in a very, very short time frame, a third alpha particle has to come, and that will form the excited state at 7.7 MeV, which is the Hoyle state. But the reaction is so rare that it needs a special experiment to set up to measure it in a laboratory.
And if we waited for three alpha particles to come together, we'll be waiting forever. So you produce that state using a proton beam on a carbon target, and that's how you make that state.
And the main transition coming down from the Hoyle state to the ground state is an electric monopole transition. So electric monopole transition is the case when no gamma ray can be emitted, a single gamma ray. It can only proceed if the energy is given to an atomic electron. This is a normal conversion process. Or very close to the nuclear surface, electron-positron pairs are formed and the two particles will carry the energy. Measuring electron-positron pairs and conversion electrons needs a special equipment. Most of the laboratories around the world focusing on gamma ray measurements. Here in a hive, we have a beautiful spectrometer to do electron-positron and conversion electron measurements. Our data is much cleaner than anybody's else before. We had a much better beam quality, we had a much better energy resolution, and a much better suppression for background. Overall, we reduced the uncertainty by factor 2 and increased the production rate by 34%.
On a big picture level, it's fascinating that Tibor found, or our team found, a tension with the accepted reaction rate for carbon production in the universe. So that means that there's still stuff that we don't know about one of the most important reactions in the universe that we really, 50 years after the discovery of the Hoyle state, we're still trying to understand.
The final results on a triple alpha reaction rate is based on three experiments. One, and possibly the most important one, was carried out here with a pair conversion spectrometer. There was a second one which was carried out also in a laboratory to measure the proton scattering cross-section and the angular distribution of the protons coming out from this reaction. That is required to analyze our data. And the third experiment has been carried out in Oslo, University of Oslo, and all the three experimental results has been combined together, and this is what we needed to get the 34% increase in the production rate.
The reason we use the NCRIS Heavy Ion Accelerator Facility at the ANU is because of its exquisite energy resolution. And these are not easy measurements because you are using a 10.6 MeV or 10.2 MeV beam, but you have to use steps of 20 keV, so 1/1000th of the energy that you're using.
The super is a superconductive solenoid which produces 2 Tesla magnetic field. The cores are here in a horizontal pipe, One end is the target. The beam comes in on a beam line and excites carbon-12. Electron-positron pairs are emitted, and the ones which going in this direction will be deflected in a magnetic field on helical path. The detector is located over here inside the vacuum chamber. The detectors can't see directly any radiation coming from the target. There is thick absorbers, but because the electrons are and the positron light particles, they can actually move on helical path and avoiding the interaction with the absorbers. And we can only see electrons and positrons.
We took our carbon and we hit it with the protons. They fused to make nitrogen-13. Nitrogen-13 will then spit out that proton, leaving the carbon in the Hoyle state, which is what we want. We need to measure where that proton goes because in T-Ball's experiment, he only measures in a certain angular range. And to do that, we had to do very high angular coverage measurements with high granularity to get that answer. But when protons scatter, they have really intricate and really interesting angular distributions because you know they're not a classical particle in a real sense, right? They have these quantum interference effects that make the angular distributions quite complicated. Of all this particular measurement came out of a discussion in the tea room. T-Ball came up and asked, "Oh, do you have a good way of measuring it? We need to know this." And we just happened to have the experiment set up and ready to go. For something else. So we were like, yeah, we can just slot you in and do this measurement. So it's a really cool example of collegiality and being agile. Very, very few labs in the world are able to be that agile.
The exciting thing about this measurement is it shows a global effort in making a measurement which is the basis of our life on Earth.
We're chasing something which is happening in the center of the stars. And of course, we can't go there with our equipment and do a measurement in the center of the star. But when we have a nice laboratory like this one, we can do an experiment and set up the same condition. We can populate the same nuclear reaction and study here in much cleaner environment. That was the most exciting thing for me to actually carry out this experiment.